With the permission of organizers, I'll start the presentation. So I'm today presenting about 3D printing. Basically, last 5 to 6 years, I'm working on fused filament fabrication based 3D printing. And I'll be dealing with that specifically here. So my research focus is additive manufacturing and multifunctional materials, metamaterials. I do fracture and fatigue of additive manufactured materials and composites, nano composite, functionally graded metals. I'll give some glimpse of this in this presentation at the last. Also, I'm working on machine learning, AI, and cybersecurity and additive manufacturing, because the crucial part in additive manufacturing is the base thing. What we are basically dependent on is the CAD file, which we convert to STL file. Now, when we are sending these STL files across the network, there is an every chance that a hacker might hack it and use it for producing the similar parts one, or else he may introduce a defect into this STL file before it is reaching to the other end, that is at the printer end. So I'm working on some cybersecurity aspects, some algorithms from computer science domain to just protect them, detect the defect, and if possible through the algorithm, we can just rectify it before it reaches to the system, that is the additive manufacturing machine, because these are things are very crucial in commercial space and more importantly in defense sector, wherein the sabotage of these files are going to play a critical role. Fine. So I'll just specifically across all the areas, I'll just focus on one, which is my area which is very close to my heart, and I'm doing the research in this for past, I think, 7 to 8 years now. So I'll just take up that. And what presently we are doing pertaining to these materials in 3D printing regime, I'll just present it as part of this. So my group basically works on syntactic foams, wherein we introduce hollow micro balloons in the resin. And these resins can be thermoplastic, thermoset, metal, ceramics, and so on and so forth. And what advantage we get it here is then we can have a property variation based on these micro balloons volume fraction one, which is generally talked about in composites. But in addition to that, for the same volume fraction, if we change the wall thickness here of each of the micro balloon, we have a different density particles and different properties altogether. So rather, this is the area wherein we have a wide range of property modulation. Need not have to be only volume fraction or weight fraction based, but for the same volume fraction based on the density, and which in turn is governed by the wall thickness of these hollow micro balloons. And that's how these are very beneficial and are being used from aerospace, automobile, and marine applications, the similar systems. So naturally, there are fly ash particles available, which one can utilize to prepare these syntactic foams, or else there are artificially manufactured particles as well. We prefer spherical over the cuboids because these have corners, wherein the hollow or other spheres don't have corners and no stress concentration effect. And in addition to that, because of the spherical particles compared to these cube or cuboids, the resin spread is always better. And more or less all the manufacturing methods from conventional to advanced can handle these spheres with equal ease. So these are there are various applications, and the applications are still evolving and pushing the limits from presently railways, aerospace, thermoforming plugs here, which are made up of foams, and then most commonly used buoyancy modules in marine systems are made up of these foams. So typically, I'm just presenting the area wherein I'll keep the matrix same, that is a thermoplastic system, wherein high density polyethylene is used. These are available in virgin as well as recycled form in the commercial space. And in this, we infused fly ash cyanospheres. These are hollow micro balloons from the, or rather, these are the environmental pollutants. These are the part of fly ash, which is an outcome of thermal power plants. So this falls under natural system, and there is artificial system also available known as hollow glass micro balloons, which are also available commercially, wherein the particle size is typically around 50 microns. Here, the particle size for cyanospheres is around 75 to 120 microns. So these particles drive. I'm very sorry. Drives the manufacturing methods do you use? Because when you mix with this any of the resin, let it be thermoset, thermoplast, ceramic, metal, and so forth, we have this limitation of particle size, and based on that, the clearances in the machine need to be identified. The clearance, what I mean by this is, if we take an injection molding machine, a critical part in injection molding machine is a barrel wherein there is a screw rotating at under 3 different heating zones. So the clearance between the screw and the barrel, based on that, we need to decide what particle you are going to use, and typically the particle size. So it is not like that we just think and then go and try. There is an engineered way to just boil down to the particle size as well. So what method you are using, what is the minimum clearance available across this manufacturing system governs the particle size. And typical thumb rule is that the 10 times of this particle size should be the clearance of that. Or other way around, 10 particles should pass through this clearance. And that is how you should finalize your manufacturing method. And the clearance, you need to relate it to the reinforcement which you are going to use. Need not have to be always with the particles, but also with any of the reinforcement, let it be short fiber or a continuous fiber, so on and so forth. So these are the typical 2 systems. And I'm just telling you how I progress towards 3D printing from an injection molding. So this is what the clearance I was talking about between the screw and the barrel. This clearance, in this clearance, minimum 10 particles should fit. And that's how we decide which reinforcement, or rather the size of the reinforcement. Typically, we decide based on that. And here is our 3D printing machine, which is based on fused filament fabrication. So filaments are fed to an extruder. This extruder has a heating element. This heating element heats the filament and then deposits layer by layer based on your CAD model. Now here, the filaments you can buy from the market, wherein you have minimum material innovation or a novelty for that particular work, or else you can manufacture these filaments based on the application, and that creeps in, or that makes the material innovation to creep in into this manufacturing method. And the fused filament fabrication, why we choose? Because this is the most commonly available, affordable system in the market. So you can get this 3D printers from, I think, 15,000 up to 1.5 CR or even 2.5 CR or up to 24 CR. Crores of rupees, based on what dimension, what materials, what the build volume you're going to print. So as this was an affordable system, we exploited that. How did my research group went from injection molding to 3D printing? Is this: we did injection molding of fly ash cyanospheres, which are naturally pollutant one, in HDP matrix, and we could able to injection mold many of these components, except this component, which is the gear. Now, if you closely look at this component, this is how it looks like. What does this tells us? That the injection molding of relatively complex components, the fly ash particles did not flow in this region. The reason which is clearly evident as with the white patches. So this white patches means the gray colored particles did not go through. Here, because there was a thick to thin section and contours, and this is where we thought of taking this defect out using a 3D printing method, wherein we can deposit layer by layer and we'll have the particles at all the cross sections to make it completely, you can say, eco-friendly component. So 3D printing technology, there are many methods. As per the ASTM, there are 7 different methods classified. One among them, as I said, as far as the cost is concerned, the most affordable one is the fused filament fabrication or fused deposition modeling. That's what we call it as. And ultimately, for all these 7 classes of additive manufacturing methods or technologies, what you need is a CAD file. This CAD file is sliced, and we call it as a standard, STL file, which is stereolithographic file, acronym of stereolithography file, or standard tessellation language, wherein triangular elements or facets are used to build the solid model. So ultimately, for all the 3D printing or additive manufacturing technologies across 7 classifications, what we need is a solid model. That solid model can be from the CAD, or you can have your own MATLAB code or some numerical data based on which you can build that. Or thirdly, if you have a component, you can scan it and convert it to a solid model. So ultimately, we need a solid model here that we feed it to a slicer, which slices in n number of layers, and that layer is been sent to a 3D printer, which prints as per that layer in which the contour is present. And it goes on printing contour by contour, one over another, to realize the final component like this. The styling feature of additive manufacturing compared to subtractive manufacturing or formative manufacturing. Formative manufacturing is nothing but our casting, forgings, and so on and so forth, is the design flexibility. Here, lead time is minimum, and based on the design changes, quickly we can feed that CAD file to a machine which prints as per the CAD file, and that is the design flexibility. So this is what method we are going to talk about today for sandwiches and functionally graded materials at the last stage of the presentation. So here we need a wire or a filament which will be sent to an extrusion head. Here it gets melted, and through this nozzle it deposits based on our whatever CAD model you're going to feed in. So these filaments are typically commercially available with 2 diameters. They not have to be the same. Based on your nozzle, you can always change the filament diameter. But in commercial space, because the machines are available with specific nozzles, presently in the commercial space, we have 1.75 plus minus 50 microns or 2.85 plus minus 50 microns millimeter diameter filaments are available. Need not have to be these. We can always have 5 millimeter filament diameter, 10 millimeter filament diameter, based on the requirement and based on this nozzle size. Typically the nozzles comes with 0.4 millimeter or 400 micron aperture, through which it will be melted and fed. So again, why I mention this nozzle diameter is, please do remember, as I said, the minimum clearance in the system decides the aspect ratio or the diameter of the reinforcement, the diameter of a short fiber or a long fiber or a particle or so and so forth. So if it is 400 microns, you know the thumb rule. So again, the particle or the diameter of the reinforcement should be 1/10 of that. So this is where always we need to have a check on. Need not have to just think fancy and try to print it. Just remember the clearance which is available in the system which you are going to use it. 1/10 of that is a safe bet for the reinforcement size to be fed, because as we all know, there might be a chances of agglomeration, or sometimes fundamentally the uniform dispersion distribution of the reinforcement in the matrix makes a lot of sense. So typically what we exploited are these 3 systems. This is a polymer blender wherein we blended the reinforcement and the matrix. Then this is a very crude level of polymer blender, which was costed at 2 lakhs. But better than this is a twin screw extruder, which will cost you around 25 plus lakhs. Wherein these twin screw extruders there are two screws in a barrel, and because there are two screws in a barrel, you will have an uniform and homogeneous distribution of the filler in the matrix. And whatever outcome comes of this polymer blender or twin screw extruder, we cut it and put it in single screw extruder to have the filament. Please do note that the outcome of the polymer blender or a twin screw extruder is never uniform. And what we need for a 3D printer, as I said, 1.75 millimeter plus minus 50 microns or 2.85 plus minus 50 microns, or any diameter based on the requirements here or nozzle diameter here, plus minus 50 microns. Plus minus 50 microns is not possible to achieve on a twin screw extruder, because in twin screw extruder or these polymer blenders, pressure variation is large. And thereby, the output, though it comes in the form of a wire, the diametrical variations are really high. So we use this polymer blenders or twin screw extruders only to blend and have a wire of a variable diameter, chop it and put it in a single screw extruder, wherein we can maintain plus minus 50 microns easily. Now, when you go for a single screw extruder, there are two types of extruders are available. One is vented type, another is non-vented type. Vented type will cost you more. Non-vented type is cheaply available. But one downside of a non-vented type is, as it is non-vented type, venting is required to take the flue gases out when you are extruding the filament, or when the blended or composite blend is been fed into this hopper. There are gases formed, air entrapment creeps in picture. So if you have a vented type, we take it out through the extruder at the die end. If you don't have it, then these entrapments goes into the filament, and also in 3D printing, these voids will creep in. This is, though it is a downside, but please do remember that though we have the air entrapments in filament, which gets transferred to 3D printed final component as well, if those are uniformly distributed, I repeat, if the defects or the voids are uniformly distributed, nothing to worry about. You state it clear and loud, and that's all. The reviewer never questions you about that. We have a single screw non-vented type, and we did quite well in the publications by stating it very clear that this is the reason, but the defects are uniformly distributed. Also, we gave an upside for that justification, as we have air entrapment, it reduces the overall weight of 3D printed component. So these 3D printed components might not be good for tensile or fatigue loading, but definitely going to be good for shock absorption, compression, and so on and so forth. So thereby, if you have a better money, good funding, you go for vented type. Not, you can settle down with a single screw extruder, but make sure that you will do a good material characterization, wherein you will have the wide or defect distribution quite uniformly well. So whenever we deal with this, any additive manufacturing methodology, for example, or in particular fused filament fabrication, you need to keep an eye about these different parameters. So during extrusion, we need to tune up barrel temperature, die temperature. These two things are typically set with a baseline property of TG, glass transition temperature should be known to you, melting point should be known to you, and polymer degradation time, temperature should be known to you. So based on that, you can have an initial start and then go on fine tuning, so that you will have a good flowability of the composite blend, which will come in the form of wire. And then the wire diameter is modulated based on the screw speed and the takeoff speed. So you can just, it is just like inducing a tension while drawing the wire out of the die. And this should be consistent enough so that you will have 1.75 plus minus 50 microns or 2.85 plus minus 50 microns, which is pretty much achievable using the available extruders which are made in India. Then pertaining to 3D printer, we have a printing temperature, nothing but the nozzle temperature many a times. Both are synonymously used. Then we have a chamber temperature. Then we have a bed temperature along with the speed. Okay, so again, these all things need to be tuned if you are developing the materials on your own for a specific application. But if you are using which are commercially available, like ABS with carbon fiber, PLA with carbon fiber, polypropylene with glass fiber, then these filament spools comes with the numbers for printing them. So there you need not have to scratch your head much, but definitely when you are developing your own system, a different system than which are available commercially, then it is going to take a quite good amount of time, but I'm not saying it is impossible. So we have extruded many filaments in the house. We never bought any filament from the market. So this is HDP filament. So we thought that nobody is working in HDP, which is high density polyethylene, which is used quite extensively. So let us try out 3D printing of that. And we were quite successful in utilizing this. So this is the filament of 1.75. Then we infused environmentally pollutant fly ash cyanospheres in that. We could able to get this. We have printed some composites, some elastomers as well. So this is the elastomer, which is used for steering wheels in four-wheelers. So we have developed some blends and printed them as well. So whenever we talk about any new material development, we need to look around the filaments first, because need not have to be filament nowadays. Even you can fit directly the pallets, because now pallet fit 3D printers are also available. So ultimately, the raw material need to be checked. So these are some initial pictures of the filament wherein we failed. The one is this, wherein you can see the non-uniform distribution. Now you can see some pockets here, some balloons here. So these balloons are made up of those fly ash. These are the failed micrographs. We did micro CT as well. So you can see filament is not rather spherical, it is in the oval form. So that is what I was talking about, tweaking the filament extrusion parameters. So with over a period of time, we could got the grip of the parameters, and then we could able to get a circular filament. And now you can see some pockets here. One, I hope you all can see the cursor movement as well. Sorry, I did not ask that earlier. So there are pockets here. You can see 1, 2, 3, 4, and you know the reason well for this. These are the pockets. These are nothing but air entrapment. And as I stated it very loud and clear, the extruder what we used was non-vented type. And thereby, this is an air entrapment. As far as this air entrapment is uniformly distributed, don't worry at all. But you need to quantify that while you are writing a paper. Mention that what is the void volume %, and equally mention that such voids will reduce the weight still further than infusing hollow microballoons. So if hollow microballoons can reduce the weight by, let us say, 25%, these void pockets will reduce it further to 26 or 27, which is not possible by infusing the hollow microballoons. And this is how we give justification in all our papers whenever we use non-vented type extruders. So these are some failed microballoons. As I said, there is a shear force which gets applied in this extrusion process. And one more parameter critically which you need to look around if you are using a hollow microballoon is its crushing strength. These are naturally available fly ash cyanospheres, thereby crushing strength is low, but still some particles failed. We reported, or you can report also the particle breakage, what is that percentage? in the system. So this is how they look like. This is one time extruded, 1x, meaning we have extruded one time, a higher magnification of this in here, and then this is 2 time extruded, and this is the 3 time extruded one. What does that mean is we extruded one time, and then we checked the recyclability potential of these filaments. We chopped these 1 time extruded filaments, extruded again, and that is 2 time extruded. Then again we chopped this 2 time extruded filament and again extruded, that is the 3 time extruded filament. Here HDP 40, meaning 40 by weight % of fly ash cyanospheres, which are hollow microballoons. You can see it here, which is a broken one, which is infused in high density polyethylene and extruded multiple times. Another way to look at is many a times what we do, we produce or we represent the scanning electron microscopes. Sometimes some reviewers are so critical that they say that, okay, you have provided us with the scanning electron microscope of the area which you were comfortable with. But reviewer says, I am not comfortable with your chosen point. I want to look at it at a more larger scale. To answer such reviewers, the best way is you can take a micro CT of that complete region. So this is a micro CT. You can see 1, 2, 3 planes here. So across plane 1, this is how the micro CT looks alike. This is how micro CT looks alike across plane 2, and this is plane 3 here. So this is how it looks alike, micro CT of that. Again, micro CT shows you the dispersion, and you can see a large voids here. You can very well correlate these large voids with here, whatever is shown in A, these large voids. Okay, that those are being seen here. But there is one particular thing which we all have to really remember about micro CT is, this is what I'm going to show that with the help of this slide. So here the fly ash cyanospheres wall is also porous. You can see the porosity within the walls. In micro CT, whenever you take, it gives one misinterpretation. Rather, we can misinterpret. Micro CT gives an actual picture, but how we misinterpret is, this is 1, 2, 3, and 4. So behind 1, 2 comes. So micro CT slices a particular material system in thousands and thousands of layers or slices. So 2 is behind 1, 3 is behind 2, 4 is behind 3. And these are apart by very few microns. So it is typically in the same zone, we have different slices. Now, when we interpret these things, where the interpretation go wrong is, if we focus on this micro balloon, it seems very intact here. Now you can see a small discontinuity here. The discontinuity has completely grown here, and again the discontinuity closes here. So by looking at the micro CT here, you may say that this micro balloon is cracked, failed, fractured, but it is never so. The reason is these inbuilt porosities which open up and close as this micro balloon you are slicing in the micro CT. So please make a note of this. Whenever you do micro CT, you may come across such observation. That does not mean the system has failed or micro balloon has failed or the fracture fiber has fractured. It might be there's some discontinuity inbuilt in the reinforcement, which you need to look around and just compare with other slices. One more thing, what we generally do in our research group is we don't directly jump into 3D printing. So we do injection molding of the similar system, and then we compare the tensile test. We do a tensile test, a dog bone sample in injection molding machine. That results are, that one result is here, okay? And then we compare this ASTM standard dog bone sample tensile test at the same strain rate for the filaments before jumping into 3D printing. So what does this say is, these lines, cross marks are 40%. This is also 40%. Okay, injection molded one. Same composition, same material, same temperature set in injection molding as well as for extrusion. So these two are wires or filaments. So this is 3 times extruded, 40% by weight of sinosphere infused in HDP. This is 2 times extruded, 40% weight fraction of fly ash sinospheres infused in HDP. So before 3D printing, we compare the filament, I repeat, filament with the injection molded completely dense dog bone sample. And we check how is the performance, because we don't want to waste neither the time of the student nor the machine time nor my time. Before going to 3D printing, we check does that make a sense, and we compare the injection molded sample with the filaments. If the filaments are doing good, only then we jump into the 3D printing. Now, as you saw, for a given strain rate, okay, strain rate is rate of loading in tension, 3 times extruded filament is performing much better than completely dense dog bone sample. 2 times extruded is outperforming the injection molded sample. So as filaments are outperforming than the completely dense injection molded sample, there is definitely a sense in jumping into 3D printing and dedicate some time for 3D printing of these compositions. And here I have incorporated one more plot. So for a given HDP 3 times extruded filament, we did strain rate variations and check how the material property changes. And we all know that every material in this universe is strain rate sensitive, meaning you change the rate of loading, the material behavior is different. So thereby, whenever we look at any plot, let's make sure that to understand what is that rate of loading, and rate of loading definitely changes the properties of the material. What does this mean is, you are wearing a shoe, shoe has a sole, you are standing, there is one rate of loading, that is compression. When you start walking, the same compressive load comes in with a higher rate of loading, and with the same shoe, when you start running for the same sole, we have a different rate of loading. And this is how the soles are being manufactured and tested for different different rate of loading. And that also we implicate for our materials development, or you can also think of that, so that you will get a broad picture of how you can enhance the properties by changing the rate of loading. Okay, so this is what our first experience, was when we started with high density polyethylene, as this material was never tested for 3D printing and not commercially available filaments, and that's why we chosen that to explore. You can see the warpage. This is the sample to be printed. When we were printing at the middle of the printing, it made the plate onto which it was getting deposited. This is also made up of high density polyethylene, because you need to have a compatible material for deposition. So this is what the warpage creeps in, and there are insufficient material flows. There are some defects here, and after tuning the parameters, as I said, printing temperature, chamber temperature, and bed temperature, along with the nozzle temperature, we could get a good sample. And this is where a good amount of time, though we follow engineered way, need to be invested to get a proper sample of new materials development. And then this is the sample of a composite blend wherein fly ash sinospheres were infused. And finally, we could able to get your ASTM, I think D635, 165 millimeter length sample, a dog bone sample, we could able to print it completely. One more point I want to just make here is, though the material is same, high density polyethylene, this is polymer injection molding, this is compression molding, and this is 3D printing. Material is same supplier, same batch, same temperature settings. So if I'm setting 160 degree here, I'm setting in compression molding also 160 degree C. Sorry. If I am setting 30 bars of injection pressure, I'm setting the pressure as 30 bars here as well. And similar correlation in 3D printing as well. Having the same material system, but if we change the manufacturing method from injection molding to compression molding to 3D printing, same material behaves in an altogether different way. Here there is a ductile failure. You can see this deformation marks which we captured with an micrography equipments or optical microscopes. Then if you take the same sample in compression molding, it is perfect crack. So ductile system gets transited to a brittle failure, ductile failure to brittle failure by just changing a manufacturing method. And if I change it to 3D printing, I get the manufacturing defect, not manufacturing, the failure pattern like this. So what does this tells us? That based on the application, you can define an appropriate manufacturing method based on what type of failure do you want. So I'll just move further for 3D printing now. So what this figure 1A shows is an image of high density polyethylene, which is typically HD 50 MA 180, which we procured from Indian Oil Corporation, Mumbai, which has having an average granule size of 3 millimeters. You can see a smooth rather texture of HDP in figure 1B. We took a micrograph of that. Glass microballoons are readily available because these are artificially made microballoons. Please do remember, when we say microballoons, means these are hollow microballoons having an average for what you see in 1C is having an outside diameter of 15 microns, as small as that, with a density of 0.6 gram per centimeter cube, and which has having a wall thickness of only 1.5 microns. So what you see in figure 1D is a scanning electron microscope of glass microballoons, wherein you can see a spherical particle without any surface defects. You have seen the Sinospheres in the earlier slide, and such defectless features of glass microballoons results in ultimately uniform resin spread around them, aiding effective load transfer, because that's what we want for strength enhancement. And these glass microballoons with varying volume fractions are blended with the HDP matrix. You can blend it with any. So this is how it looks like. So we prepared a blend of HDP and glass microballoons using a polymer blender or a twin screw extruder, whichever you have available with, to develop a feedstock foam filament for 3D printing. And then we exploited that for cores and sandwich composites. And this blending is carried out at a suitable speed of, as far as our pilot studies were concerned, at 10 revolutions per minute at 160 degrees C, by varying 20, 40, and 60 volume fraction of glass microballoons in HDP. And these different volume fractions are denoted in subsequent slides as capital H20. H is for HDP, 20 is 20 volume fraction in HDP, H40 and H60. So HDP pallets of H20 to H60, which were the outcome of twin screw extruder, were dried at 80 degrees C in an oven for 24 hours, because we want to remove the moisture if it is present any before gravity feeding into the hopper of a single screw extruder. Now, you know why we are using a single screw extruder. I did mention that in one of the earlier slides. This is to draw the filament of an appropriate size. So again, there in single screw extruder, either they come up with 3 heating zones or 4 heating zones. So you need to maintain appropriate temperature. And when I say appropriate temperature, meaning you need to really bother on the glass transition, melting, and degradation temperature. As per that, you set it properly. You set the takeoff speed and the screw speed, and to have either a 2.85 or 1.75 plus minus 50 micron diameter. Please do remember why I'm stressing again and again on plus minus 50 microns is because the requirement for a 3D printer is this. If there is a variation in this, you will have non-uniform deposit when you print it many times. The nozzle gets clogged because of the overflow of the material. So all these been chosen by considering HDP melting temperature as a of glass microballoon in HDP, definitely without breakage. And what is that without breakage? You know very well now. You know the minimum clearance, and you know the typical thumb rule that at least 10 particles should pass through them comfortably. And now please do remember, 10 particles meaning it is not that one particle getting touched to the second and in a row 10 particle. No, you have, I think we all know that we follow the rule of d by 2 on either sides in machine design for design of machine typical fastening elements. So same thing has to be here. So what I mean by this is your clearance should be equal to d by 2 plus d by 2 plus d by 2 plus plus d by 2. Likewise for 10 particles and then plus d by 2. So in a row, once you add all these, should be your nozzle diameter or the clearance, the minimum clearance which should be available with the machine as a typical thumb rule in processing. Let it be a short fiber, continuous fiber, or a particle. So what did we observe is with an increase in GMB content, because these are hollow microballoons, wide percent do increase because we have a non-vented type. And why wide content increases? Because the rheology changes as when you put on more reinforce in the matrix. And typically you can find out that wide in our studies with this glass microballoon infused filament or 3D printed components which were lighter in weight up to 28 to 30%, which is a substantial reduction in weight without compromising mechanical properties. We did observe the wide percentage of around 0.8 to 8%. For extruded H2, H60 filaments. So these are, as I mentioned earlier, you can eliminate these voids completely if you can use the vented type extruders. But if you have a non-vented type, these additional porosities, if they get transferred to the printing samples, which we did observe for a three-phase syntactic foam. A three-phase means one phase is matrix, second phase is hollow microballoons, and the third phase is now wide air entrapment, which is present there. These might enhance whenever we have a three-phase syntactic foams, this enhance damping capabilities. So what you see in figure 2A is a circular cross-section of an extruded H60 filament, and you are able to see some mark here, right? This mark is because this filament could not be fractured or rather could not be freeze fractured. What do you mean by freeze fracture? Is you put the material in liquid nitrogen for a day or a two, we kept it for a week, but still we could not able to fracture it in a brittle manner because we wanted to see what is the microstructure here or what is the morphology here. So ultimately we took a knife, and this is the knife mark. My student pressed hard, but by the time it reached to this point, he left the load, and that's how it creates a mark. And then again, he pressed it. So this is the reason for this step formation. It is because of the uneven cutting forces or shearing force we applied when we were chopping it or cutting it with the help of a knife. So H20 filament at higher magnification shows a uniform dispersion of GMBs in this 2B, and you can see these lines. This is matrix flow lines. These are in the direction of the application of knife force. Now the extruded H60 filaments, you can see it here, and typical properties of HDP granules, which we bought it from Indian Oil Corporation Limited, are mentioned here, okay, for your reference. So then we did the sandwich part, and we took the help of finite element analysis. So as we all know, the sandwich structure consists of a skin, upper and lower, and the core, the middle position. The printing parametric optimization was carried for the core first, being thicker. We need a multiple printing layers there. The filaments have the composition of, as I mentioned earlier, H to H60. Fed to fused filament phase fabrication-based 3D printer. Any printer will work out. But there is one thing you critically must remember. It's the printers are basically categorized or sold based on the build volume, number one, But whatever minimum build volume you take, I think minimum build volume are available of 150, 150. Better to go for is 250 by 250 because your ASTM standard tensile dog bone sample, I think type 4 or type 1, I don't remember exactly, goes for a length of 165 millimeters. You can also go for 100 by 100 or 150 by 150, wherein you can use a type 1, wherein the length of the sample is really good. So please remember, you look at your ASTM standards and the sample dimensions there, that will tell you what should be the build volume or typically the build plate, that is XY. So printing volume in XYZ, anyway, all the printers support, but printing in XY direction, that is in a horizontal plane, is very crucial based on your ASTM standards. So look at the ASTM standard, and then decide on the XY direction printing, and then buy a printer based on the printing temperature you want. So if you are using PLA, ABS, I think 260 is more than sufficient. But even for HDP, 220 is sufficient. But if you are going for polyether ketone, you need to go really high, many times, and sometimes for foamed filaments, 260 is also not sufficient. And whenever the temperature goes up for nozzle for printing, you must have an enclosure. There are many printers available on Amazon or so on and so forth, which are based on open architecture, wherein there is no enclosed chamber. You can also make it an enclosed chamber made up of acrylic, but you many a times for high performance polymers, we or even for polymers, regular polymers with carbon or glass fiber, or sometimes for continuous fiber in post system, we must maintain a chamber temperature. So you need to set a little more amount to go for it. So while buying a printer, please have or make a note of this so that you can utilize a wide range of materials to be explored. So here, what we did is, as we all know that typical printers comes with 2 nozzles. So we utilize both these nozzles for printing the composite or sandwich. So we know that the filaments are melted in a nozzle, head of the printer for layer deposition. And as there are 2 nozzles, I can designate that a primary nozzle as N1, N is for north. So secondary nozzle is for N2. So typically the secondary nozzle is being used for printing support materials. So as the ASTM sample geometry is very simple, we need not have to go for support material, and that's why we thought that let us feed another filament of composite in N2 to print multifunctional, multi-material system like in sandwich composite. And here the philosophy was, as we all know, the conventional sandwich manufacturing is like we manufacture the core separately, and then we prepare the sandwich by putting the skins at the bottom. We soak it in a thermosetting resin. We place it in a mold, and once the desired thickness of the skin is reached, we keep a core which is already manufactured by some other method. And then finally, we form the upper skin. And once the upper skins are formed, we close the mold. We keep it for 24 plus hours so that it cures. And then we take it out, we trim it, and we test it. But here, in conventional manufacturing method, the prominent failure phenomena which occurs is debonding between skin and the core. And this was the major disadvantage of these conventionally manufactured sandwiches. So we thought that let us completely eliminate that by printing a sandwich at one go, all at once, so that we will not have any delamination between the skin and core, and that we did achieve it. And especially when we want to print the sandwich with complex geometry, conventional manufacturing method poorly exhibit the properties, but in 3D printing, as it has a design flexibility, we can exploit rather realization of these complex geometry sandwiches quickly. and that too without any delamination between the skin and the core. So that's how was the philosophy behind printing the sandwiches here. So we utilize both the nozzles while printing the sandwich. And while printing sandwich, N1, North 1 or primary nozzle deposits the lower skin, which you can see it here. So this gets deposited by nozzle 1. And once the printing is done, then nozzle 2 has a core filament or the filament to be utilized for core. It completes, the nozzle 1 completes 1 millimeter. Then nozzle 2 completes 6 millimeters of height I'm talking about. So total 7 is done. And then again nozzle 1 comes in and starts printing the skin. Please do remember, all these things are manufactured all at once. What does this mean is we have cut down the lead time of manufacturing of sandwich. We can print sandwich of any complex geometry, and all at once, most importantly, means the interface between the skin and core is more firmly bonded, wherein you can anticipate that there is no shear failure or delamination between the skin and core. And that is what we did. We manufactured these sandwiches, what you can see it here, of having core of 20% glass microballoon infused high density polyethylene, then 40, then 60, and we named it as SHS for South, H for HDP. So SH20 means 20% of glass microballoons by volume in HDP matrix and the sandwich of it. If I say H20, it is only the core. And if I say SH20, it is the sandwich made up of H20 core. And that is how you will see in the subsequent slides, the naming is been done. Then we thought to have, as this slide shows, a finite element for just to look at the stress distribution across the sample. So here, the 3D printing, as we all know, involves a complex heat and mass transfer phenomena that affects the dimensional accuracy of the final part because we are printing at an elevated temperature. So the thermomechanical finite simulation are carried out using ANSYS. We had 2020 R1 version and suitable printing parameters, which we finalized in printing as boundary conditions were fed to visualize only the temperature and thermal stress distribution. We didn't do elastic plastic analysis here. Only the thrust was to just see a temperature and thermal stress distribution because of printing at higher temperature. So what we did, we carried out a three-dimensional steady state thermal analysis, and the temperature distribution is used as the load input. The temperature of printing has been fed for static structural analysis. We used a hex 20 element having an element size of 1 millimeters. And in pre-processing, the properties of skin and core were defined, and then we fed them. I think those properties are available here in table 3 for as far as density, CT, thermal conductivity are concerned. And the sample what we printed and utilized for finite element analysis was having a length of 180 millimeter in length, 18 millimeters wide, and total 8 millimeter thickness. Wherein 1 millimeter skin on bottom and top are out of these 8 millimeters. So core is about 6 millimeters. And we kept, while printing, we kept the layer thickness of each layer, because we all know that in 3D printing, we deposit layer by layer. So we kept the layer thickness is constant as 500 microns. So in total, there are 16 layers. The same has been also modeled in 3D printing. So before meshing, sandwich elements like skin, core, and skin are coupled for effective heat transfer. Figure 3A here and 3B present the sandwich finite element model and the mesh respectively, the convection boundary conditions are imposed, as you can see it in figure 3C here, and the subsequent analysis was carried out for temperature distribution, and then the obtained temperature data is taken as a load data for static structural analysis. To observe again, I reiterate, to just observe a stress distribution in 3D printed samples. So the pilot investigations are carried out using these actual range of temperatures which we utilized for the 3D printing. So we, as I was telling earlier, that for printing core H20 to H60 and sandwiches, we exploited nozzle 1 and nozzle 2. Available in any of the commercial fused filament fabrication based printers. I am using fused filament fabrications intentionally because fused deposition modeling is a copyrighted word, and thereby in our research group, we or while communicating the journal papers, we never use FDM. We always use fused filament fabrication because this is synonymously used for FDM, and this is not a copyrighted word, wherein FDM is. So try to avoid using the copyrighted words because many times reviewers get fumed that they feel that we or the authors are even don't know which are copyrighted and why, and you know that legal complications comes in. So I always use fused filament fabrication. And in your cases also, whichever additive manufacturing methodology you will use, you just check whether it is copyrighted. If it is copyrighted, avoid using them. There are other names for similar term which you can definitely use it. So next, what we did, having these parameters, next crucial thing in 3D printing is the substrate selection, because when you want to develop a material system which is not available in the commercial market, you have to dig each and every hole because you need to find out what is that build plate in a 3D printer onto which you're going to print it. And it is same for any material system. Let it be paste extrusion, inkjet bag, inkjet printing, binder jetting, or even direct energy deposition or powder bed system. We need to critically evaluate those whenever we want to develop a different systems and look around that. So the selection of a suitable substrate for printing core and sandwich is very crucial because the first layer which we deposit has to adhere to the base until the printing is done, and need not have to until the printing is done, until the sample gets cooled completely within the chamber or within the build volume, whatever additive manufacturing method you are using. What does this mean? I'll show you in the subsequent slides, wherein we did observe that until final layer gets getting deposited, everything went perfectly fine. But when the sample starts cooling, the warpage creeps in, especially for such multi-material, multi-functional materials, wherein the sample completely gets lifted off and bends permanently. So it is not like that we need to just bother about adhesion of the first layer to the bed until all the layers are getting printed. It is until the cooling of sample to the room temperature. So that is very crucial. And in our study for high density polyethylene, what we observe is Kraton ACBS polymer is the perfect with bed heating. Again, here you need to tune the bed heating parameters. So that is how it goes. And then about if we need to talk about the adhesion, I'm going to talk about different parameters here. So the adhesion bonding between the first layer of the print and the substrate depends on the bed and the chamber temperature. So again, please do remember, if you want to utilize your printer for a wide variety of materials, though it is going to cost you a little more, go with the enclosed chamber so that you can utilize many material systems for a quite longer period of time. So if you look at this figure 4 and A part, which can be seen here, I'm going to talk about a little bit about this now. So these are the representative print images after peeling the samples. Peeling meaning removing the samples from the substrate at different bed and chamber temperatures. The improper adhesion results in non-uniform surface texture. In case of 80-degree, when you set the bed temperature as 80 degrees, and for chamber temperature between 45 to 75 degrees. Now, if you increase the bed temperature to 100 degrees C, improper raster diffusion at the base layer forms a very rough surface, and there are some wide formation possibilities. Now, the perfect bonding, uniform texture, and good quality sample without any defects, we could observe when the bed and chamber temperatures are maintained for 120 degree and 75 degrees C, as you can see it in figure 4A. Please do remember, these numbers do change when you change the matrix material, when you keep the matrix material same, but when you change the reinforcement. So you need to tweak in when you go on an exploratory mode. So the uniform and same texture on bottom and uppermost layers of the printed samples are very crucial to render especially a similar stress state under a given applied load. If the stress distribution is non-uniform, then that is the region wherein the crack initiates, wherein there is a high stress concentration and the material fails earlier and its load carrying capacity drops down drastically. So this we need to take into account when we are designing an experiment, when we are designing the material system, and ultimately when we are processing it. And that's how the finite element simulation, we took the help of it. So the chamber temperature, again, as I said, plays a vital role in controlling delamination at skin core interface, which you can see it here in figure 4B. Now, the delamination is significant in high density polyethylene and their foam prints. We did observe that with larger dimensions, because these are very small dimensions, though not so small, because length is 180 millimeters. It is quite well. But if I extend it to 250, again, I need to tweak in these parameters, please. So, in such cases, for 180, you might not observe the delamination, but 150 for the same printing, suitable printing parameter, which you say is, yeah, we achieved it. But when the dimensions change, we need to little again tweak in there. So these are some of the parameters, some of the parameters which you can really look into. So we need to set an appropriate chamber temperature as well to reduce the temperature gradient, which will affect this delamination. So as seen from 4B, below 75 degrees C chamber temperature, delamination is observed at the skin core interface and within the layers also. The visual observation by after post printing and the micrograph as presented in C, you can see here a micrograph, a nice micrograph. These are the layers, and you can see the delamination here. This is the skin and this is the core. This core is a foamed one. So these are the many of the parameters which creep in when you go for multi-material systems. And thereby we need to really look for a micrograph, something like this, which is definitely possible with patience, and with some extra amount of time, it can be always possible to navigate to a best sample. I'm going to talk about now the flow of material during printing. So in printing core and sandwich structures, the flow of material from the nozzle again decides the volume of the material to be printed. As we know that there are two nozzles were exploited. So nozzle temperatures And one more parameter comes in picture here is known as an extrusion multiplier. These two affect the material flow. So the temperature of N1 varies from 200 to 230. Now you have seen that in table 2. I'll just go back to that. Yes, here 200 to 230. So this 200 to 230, N1 carries the FDP filament. So we held it at 200, which results in non-uniform layer deposition. You can see this in figure A. The temperature of 230 enables more material flow, leading to bulk material deposition at different locations. One such location of bulk deposition is clearly marked in figure 5A here, and these things are need to be resolved. N2 is maintained at also 200 to 230 for printing the foam filament. So in nozzle 1, we have an HDP filament. In nozzle 2, we have a composite filament. So a similar observation is also we could able to see as observed during printing HDP through N1. So nozzle 2 is set at 225 for printing. Figure 5B typically shows representative print images of H60, as this combination has the maximum GMB content. That is, it has the lowest content of matrix across the chosen compositions. We did not go beyond 60 for the obvious reason that based on our pilot studies, what we've seen is there is an agglomeration, filaments get rough, and when the filament gets rough, it is brittle. And again, the diametrical variation goes beyond plus minus 50 microns, wherein the printer clogs, filament jams, and that's how we limited 60% volume fraction in a high density polyethylene. That equally means that 60% of high density polyethylene you are saving in each component weight. And we could give a picture of eco-friendly, and because we are having 60% lower polymer consumption, and the carbon footprint analysis of that. So you can give a different flavors when you try to save a material. So here also, as expected, due to lower HDP content in H60, small pockets, as you can see in figure 5B, are formed at several locations, which signify that the metal did not get deposited. And this is because the viscosity, rather higher viscosity of H60 because of much lower material flow index as compared to other compositions. So to counteract, we need to increase the flow of the material, and we need to increase the there are two ways to increase the flow of the material. One, you increase the temperature of nozzle 2. We set it at 250. Then the higher nozzle temperature made the material to flow out continuously, but with lump deposition at several locations. So again, we need to lower by 5 degrees, and these are all trial and error methods which you can always do. And also, based on this, we need to modify the extrusion multiplier. Also, this is another term when you are operating fused filament fabrication. Typically, I have chosen fused filament fabrication even for today's presentation. The reason being, this is most probably all this available now in cross as part of the tinkering lab, there was some product realization lab, the training for the first year students about 3D printing. So there's another parameter known as extrusion multiplier, which is nothing but the volume of metal flowing out of the. So for what during our experiments, we were able to find the different numbers for different composites, which are readily available there in our publications. And that is another parameter which we can always count on. So there is one more aspect comes is known as a prime pillar. So here, typically all these parameters you need to look at it carefully when you're going for multi-material system. If you're going with a single material system like ABS PLA, don't worry about it. But when you want to scratch it for something additional things and go for multi-material, multi-functional systems, all these parameters need to be looked carefully. So it will take time, but at the end of the day, there is definitely worth satisfying efforts to just look around all these parameters, tune the machine for printing were proposed material system which you want to explore. So here again, printing of sandwich structure using, as you know, using single nozzle is also possible. If you have a printer with a single nozzle, I'm not saying that you must have two nozzles for a printer. If you have a single nozzle, still you can print a multi-material system. But only thing is that once one layer is done, you need to remove the filament and put the second filament. And how fast you can do it, that ultimately transfers to good quality print, and that is definitely possible. We have done it. So I'm not saying if you don't have a dual nozzle system, you cannot do it. You can definitely do it. Okay, if you have it, you just explore it. It is definitely possible. So here, the prime pillar is nothing but some additional material which we print before printing an actual sample. Why we print an additional material, though this is not going to be of any use, this is to just make sure that the material flows out good for an actual sample. So you can always utilize this prime pillar for going for a multi-material system to have a good flow. Okay, now let us talk about a very crucial element, that is warpage. And this happens quite often when you are going for a multi-material system. Please do remember, when we say multi-material system, meaning two or more different materials you are printing at once over one another. What does that mean is, both of these materials have a different material properties, and critically the coefficient of thermal expansion. Because these two metals have a different coefficient of thermal expansion, warpage is bound to come into picture. So always you need to have CT values of materials which you want to print it. Once you look at the CT values based on their difference, you need to increase the chamber temperature so that the temperature gradient is going to be really in a very narrow range to have multi-material printings. So similarly, we also did here with the help of CTE. So this is about only the core. You can see 80 degree, 100 and 120, it was perfectly flat. Now what happens to sandwich? Yes, for sandwich at 60 is 60% by volume of glass microballoons in HDP. Here what happened? This warped, you can see this image here, this warped after printing. In other words, during printing until the final top layer, nothing, no warpage was seen. Once the last layer's printing is done and the sample was getting cooled in the chamber itself, it lifted up from the ends. And what was the warpage? You can see here, it is 30 millimeters. Then we reduced it to 10 millimeters and then perfectly. Please do remember, these values will change. You need to tweak in based on the material system which you are going to explore in due course of time. This is one more parameter. Please do remember, these are all additive manufacturing systems are mechanical systems. So we need to calibrate, recalibrate frequently. What we do in our lab is every week, at the end of the week, we again recalibrate. We make sure that the distance between the two nozzles is maintained properly. If it is not maintained properly, what you see is this. Okay, wherein you can see one layer getting additionally deposited, or there is an offset. So with offset, without offset, and these also form some lines, some voids. And finally, you can definitely restore defect-free print, but make sure that these things will come in picture clearly whenever or need to be looked into very, very, very carefully when you're talking about. So what this slide shows is freeze fractured micrographic, and this is SCM typically taken on sandwich using suitable printing parameters. Now, what does this mean? I'll go back to that table wherein, yes. So we have lower, higher, and in brackets suitable. So when I say suitable printing temperature, meaning whatever as mentioned in the bracket. So this takes a good amount of time because you need to go on eliminating one defect at a time and then work on to the next. So once we print it with a suitable printing parameters, you can see a lower skin and a core, and you can see the transition between these two. As there is a seamless interface between a skin and a core, in the core and the skin, definitely there is not going to be a delamination between the skin and the core, which is a most happening phenomena in conventional sandwiches. So with that thought process we worked on. This is lower parameters, and here you can see clearly there is a skin part, there is a core part. Core is not diffused properly. This is one layer, this is second layer, and you can see the gaps here. No doubt these gaps are very good when you want an additional damping or shock, but the interface should be a seamless, which we did. And this is what a multi-material, multi-functional material all at once with minimum lead time, with no delamination, which you can do it with a regular printer which you have in your institute. And this is on the thickness. So we have a skin and a core. This is across the thickness when we break it. Then we did thermomechanical analysis. I'll take another 10-15 minutes. Hope I have that time available to me. So the results of thermal analysis in the form of temperature distribution, as I was talking earlier, are presented in this figure, wherein this shows the temperature distribution. We wanted to just know how the temperature and stress varies for this multi-material system. So it is observed that the temperature distribution varies from skin to core, since convective heat transfer boundary condition is applied, wherein chamber temperature is set at 75 degrees. The bottom skin is going to have a temperature slightly more than the bed temperature, definitely, because we have a higher printing temperature than the bed temperature. On a similar side, the top layer of the skin is subjected to 225 degrees C based on our table and the suitable printing temperature. So the sequential deposition of the material is observed clearly in the thermal analysis, wherein you can see that distribution also present in these colored maps. Cyclic cooling and heating of the extruded metal can be seen as the temperature distribution is minimum at the bottom and maximum at the top layer, but natural because of sequential consolidation, sequential cooling. And as the heat gets conducted between the layers, the bottom layers are cooled and heated cyclically. The highest temperature, needless to say, to be noted for the just deposited layer, whereas the side faces of the sandwiches are cooling at a faster rate due to convection. Now, the temperature distribution along the thickness of the sample is, you can see that in figure B here. The temperature distribution of the printed samples mainly, we all know that it depends on heat transfer coefficient of the surrounding air, nozzle, bed, and definitely so that the temperature gradient is made. No? By considering all these parameters as the boundary conditions, a steady state thermal analysis, as I was mentioning earlier, temperature variation is observed along the thickness and also in the radial direction. The variation of the temperature in the radial direction is due to typically a convective heat transfer at the lateral edges. In it to be the core temperature as compared to the top skin, bottom skin, and also at the skin core interface. The bottom skin is in contact with the printer bed, which is maintained constant at 120 degrees C during printing. Now, due to a sudden decrease in thermal conductivity at the skin core interface, because as I said, skin properties are different, core properties are different. There is something known as stagnation effect creeps in. It raises the temperature at the top layer and interface as compared to the first layer of the bottom skin. Now, the hollow GMP particles used as the filler, as we all know, in the core have lower thermal conductivity, increasing the conductive resistance, which you can see in, I think, here in 10D. The maximum temperature is observed at the top skin because it is the last layer being deposited. So the thermal analysis results of this sandwiches is imported as a load data for analyzing the thermal stress distribution. And we applied similar boundary conditions. And they are imported for thermal analysis or structural analysis in addition to frictionless support for the bottom surface. Now, what did we observe is stresses are found to be maximum in top skin near the lateral surfaces and minimum at the core, which you can see here in figure 11A. Now, the temperature and stress distribution along the thickness of sandwich, you can see in B. And we can clearly observe the temperature distribution through the thickness of SS60 or for that matter any sandwich. So temperature increases from the bottom to top through the foam core. The bottom and top skin's proximity towards the bed and nozzle. Bed is because maintained constant at 120 degrees C, and nozzle is at very elevated temperature of 45 to 25 degrees C, are naturally seen in this distribution. So the thermal stress in the top and bottom skins are more as compared to the core due to respective thermal properties of the skin and core, in addition to the resistance offered by the GMB particles. The stress in the bottom skin is dependent on the bed temperature because bed is maintained constant at 120. The higher thermal stresses in top and bottom skin as compared to the core is due to associated temperature difference between all these systems while printing. So due to change in, this is basically due to change in thermal expansion values at the skin core surface, a sudden drop of thermal stress is observed across the interface. And this gives us a clear idea that how the temperature distribution takes place. And if at all we can reduce this gradient, especially across this 1 and 2 and 3 and 4. And what does it tells us that during this printing going on, if we can employ an additional cooling element or heating element as required based on the material system, we can employ that on a printer bed and try to reduce that gradation and probably increase the load carrying capacity. So ultimately, why did we take an FE simulation help is these FE simulations help in visualizing the stresses at the critical locations, and such locations are at presently at skin core interface where in stress level changes drastically. Though the simulation did not show any warpage as expected because we removed that warpage, right? By having all the parameters tuned up, we printed it and we just inputted that parameters to just look at the temperature or stress distribution so that in the next line of materials development, which is of multi-material, multifunctional in nature, we can just take the help of FE simulations first, look at the stress distribution, look at the temperature distribution, and if needed, try to cut it down by employing local fans on the bed so that we can have a good property or good, you can say, sound quality of the prints, I mean, better multifunctional system. So that's how we just took the help of finite element simulation. And in addition to that, in another couple of minutes, I want to just show a few of the things which we progressed further So we did functionally graded code sandwich here. You can see the same material system, H20, H40, H20, H40, H60. We printed them. We took the micro CT scan, and you can clearly see the change in the color and seamless interface, which is perfectly parallel to the horizontal plane. So we can print functionally graded material using a conventional, which is regularly available printer at an affordable cost. Further, we went into sandwich. So we have a sandwich with a graded core now. Then we just expanded our material base, and all these things are manufactured in-house. We blended the nanocomposite, we drew the filament, we printed the nanocomposite and the graded version of that. This is the foam version. This is the nanocomposite version. And there are many other things we exploited further. We use the same 3D printers for printing the panels for acoustics, which absorb the sound wave very efficiently. These panels are biodegradable and very lightweight with micro perforation, which is possible only in 3D printer, because we can have such straight holes drilled using a micro machining technique, but definitely not this structure, neither this nor this. Forget about the spherical pores. So we did also spherical pores micro perforated panels and the graded versions of that. So sphere diameter increases slowly from one end to the another end. The basic intention is to just make sure that the sound wave spends a good amount of time while there is a change in cross section. And these results are available in applied acoustics. You can go through if you are interested. Further, we did some work on orthopedic region also, wherein the mandible we printed mandible and cranial segments with bioactive glass. And we did, as I said, though the base material is same as HDPE, but when you utilize a different filler, then again we need to talk about the underfill, overfill, poor adhesion, clogging, and come across a good strategy. Then we did the warpage analysis, and finally we printed the mandible and the cranial segments also. The details are available in composite. Thanks. If there are any questions, please let me know. Or if you have any questions, even which comes to your mind at a later stage of time, my email ID is on IIT Mandi website. You can always contact me. Thank you. I thank the organizers, and if there are any questions, I'll be happy to take.
Thank you so much, sir, for the wonderful talk. Now the floor is open for question and answer session. I request the participants to please post the question in the chat box, and participants can also unmute and ask their question to the guest speaker. Now.
As I said, whenever you feel, if you have any questions, I am always able to reach on email ID. No issues that. If you have any, I can answer it here. No problem about that.
Sir, you can share your email ID with our
Oh
participants.
yeah, sure. I can put that in the chat box itself. Yes,
Yes.
yes. That is correct. Sorry. Mandi.ac. Yes, I posted it. Is it correct? Yes.
If there are any questions, please post it. Sir,
Okay.
there is a question from Mr. Shankarappa.
Yeah.
Question is, I'll read out for your reference. Is it possible to produce nanostructures on metallic substrates using 3D printing?
Okay.
Is it possible to produce nanostructures on metallic substrates using 3D printing? So this is the question.
Yes, it's possible. It's possible. It is possible. We need to go for a hybrid additive manufacturing method. It is definitely possible.
Any other questions, dear participants?
Thanks.
Sir, since no other questions are coming up, I think we will try to conclude the session.
Yes, sure.
So it's an honor for me to propose the vote of thanks on behalf of Department of Mechanical Engineering, SJAC. I would like to thank Professor Mrityunjay D from IIT Mandi, Himachal Pradesh, for presenting and delivering a lecture, a wonderful lecture on 3D printing. Truly, it was a wonderful and great session. I also thank all the participants for your active participation and also asking few questions in this session. I'm sure this session has already enhanced your knowledge. Thank you so much.